welcome to True Projects. In this video, we are going to explain the project Effective Multitask Deep Learning for Internet of Things Malware Detection and Identification using Behavioral Traffic Analysis. Introduction. In this initiative, we focus on safeguarding our ever-growing network of smart devices. With the rise of Internet of Things in homes, healthcare, and more, ensuring the security of these interconnected gadgets is crucial. As technology advances, so do the risks. We delve into the realm of malware attacks, studying notorious instances like the Mirai botnet. By understanding these threats, we aim to develop effective countermeasures. This project has a dual objective. Firstly, we are developing robust security systems tailored for Internet of Things devices. Secondly, we are creating a classification system to identify the specific type of malware targeting these devices, offering a more precise defense. And we are using machine learning and deep learning in this project. Our goal is to equip computers with the ability to learn and adapt autonomously, reducing dependence on constant human intervention for security updates. And we are introducing the innovative multitask LSTM-based model, a sophisticated solution that not only detects potential threats to Internet of Things devices, but also identifies the exact nature of the threat. It is a cutting-edge protector against evolving cyber attacks. Objective of the project. So, as I mentioned earlier, the project aims to create sophisticated systems capable of identifying and stopping emerging malware threats targeting Internet of Things devices. This involves implementing advanced algorithms and models to enhance the security posture of Internet of Things ecosystems. So, this involves creating a system that can not only identify if a given network traffic is malicious or benign, but can also categorize the specific type of malware involved. This fine-grained classification enables more targeted and effective response strategies. Unlike traditional machine learning, which struggle with the nuances of Internet of Things traffic, the project utilizes long short-term memory, that is LSTM networks. These deep learning techniques are adept at processing sequential data, making them well suited for the time-sensitive and dynamic nature of Internet of Things network traffic. And to recognize the varied landscape of Internet of Things devices and the evolving nature of cyber attacks, the project incorporates dataset heterogeneity. This reflects the diversity of network technologies and cyber threats, making the system more adaptive and capable of handling different scenarios effectively. And to bridge the gap between theory and practice, the project focuses on providing tangible solutions. The multitask LSTM model not only ensures security by detecting intrusions, but also considers the practical aspect of classifying diverse malware types. This approach acknowledges the real-world challenges faced by Internet of Things environments. Requirements needed to execute this project are software requirements. Software needed is Anaconda, primary language used is Python, front-end framework used is Flask, back-end framework used is Jupyter Notebook, database used is SQLite 3, and front-end technologies used are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements needed are operating system of Windows, processor of i5 and above, RAM of 8GB and above, and hard disk of 25GB and above. Now we'll discuss the working modules of flow of work. So the first step is importing required packages. In this step, we will import essential libraries such as NumPy and Pandas for data manipulation and analysis, sklearn for machine learning and data pre-processing, Matplotlib and Seaborn for data visualization, and TensorFlow Keras for deep learning. The second step is exploring the dataset. So here, a comprehensive examination of the Internet of Things 23 dataset is conducted. This involves understanding the dataset structure, features, and inherent patterns related to Internet of Things network traffic. Insights gained during this phase inform subsequent data processing steps. The third step is data processing. So by leveraging Pandas data frames and Keras, the dataset undergoes pre-processing. This includes handling null values, dropping duplicate entries, and removing unnecessary columns. The objective is to refine the dataset, making it suitable for effective analysis and model training. The next step is visualization using Seaborn and Matplotlib. So Seaborn and Matplotlib are employed for data visualization. Plots and graphs are generated to provide a visual representation of patterns within the Internet of Things network traffic data. Visualization aids in identifying trends, outliers, and potential features for model training. The next step is label encoding using label encoder. So here, categorical data within the dataset is converted into numerical format using label encoder from sklearn. This step is crucial for machine learning model training, ensuring that algorithms can process and learn from the data effectively. The next step is feature selection. So selecting relevant features is vital for model efficiency. Through select percentile with mutual information classify, the most informative features are identified. This step enhances the model's ability to detect anomalies and patterns in Internet of Things network traffic. The next step is train and test split. So here the dataset is divided into training and testing sets using sklearn functionalities. This split allows the evaluation of the model's performance on unseen data, gauging its ability to generalize and make accurate predictions in real-world scenarios. The next step is training and building the model. So the core of the project involves building a deep learning model, specifically an LSTM network for intrusion detection. This model is trained on the pre-processed dataset to recognize patterns indicative of potential security threats in Internet of Things network traffic. And in the next step, as an extension, the project incorporates advanced techniques such as convolutional neural network (CNN) and a hybrid model. This hybrid model combines predictions from multiple individual models, enhancing the accuracy and robustness of the final intrusion detection system. And the project extends beyond model development, incorporating a Flask web framework with SQLite for user authentication. This ensures secure access to the system, allowing user testing and interaction with the intrusion detection features. So after signing in, users are provided with a front-end interface to input feature values for prediction. The given input undergoes pre-processing, including handling null values and duplicates, aligning it with the model's requirements for effective analysis. And pre-trained models are then employed to predict outcomes based on user inputs. The deep learning models play a pivotal role in identifying potential threats within the provided Internet of Things network traffic data. And the final predictions are presented through the user-friendly front-end. This interface provides users with a clear understanding of the results, facilitating analysis and interpretation of the intrusion detection system's outcomes. Now we'll understand about the algorithm used. So we have used LSTM in this project. So LSTMs, that is long short-term memory networks, are a type of neural network designed to handle the challenges of understanding sequential data, making them ideal for analyzing time series data like Internet of Things network traffic. What sets LSTMs apart is their ability to capture long-term dependencies and remember essential information over extended periods. In the context of this project, where the goal is to analyze diverse and dynamic Internet of Things network traffic, LSTMs excel at recognizing intricate patterns and anomalies, ensuring a robust intrusion detection system. Their architecture enables them to retain valuable insights from the past, contributing to the accurate identification of potential security threats in the evolving landscape of Internet of Things communication. Now we'll see the comparison graphs. So this is the horizontal bar graph comparing accuracies of different algorithms. In this graph on x-axis I have accuracy scores and on y-axis I have algorithm names. So accuracy measures the overall correctness of predictions, showing the percentage of correctly classified instances. And this is precision scores comparison graph. In this graph on x-axis I have precision scores and on y-axis I have algorithm names. So precision measures the accuracy of positive predictions, indicating how many predicted positives were actually correct. This is recall scores comparison graph. In this graph on x-axis I have recall scores and on y-axis I have algorithm names. So recall measures the ability to identify all relevant instances, showing how many actual positives were correctly predicted. And this is F scores comparison graph. In this graph on x-axis I have F scores and on y-axis I have algorithm names. So F1 score combines precision and recall into a single metric, balancing accuracy and completeness in predictions. So the algorithm which is best performing in all the performance metrics will be used for predictions. Execution of the project. To execute this project, first we need to open the code folder which contains the project source code files. So this is static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML pages. And these are model files which contain algorithm information. These files will be loaded into the project code during runtime to utilize the trained models. And this is IoT 23 dataset file. This contains the required dataset with class labels on which we will train the models. And this is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information. So now copy the path of the code folder from the address bar of the file explorer. I am copying it. Open Anukunda prompt. So use the command cd followed by a space and paste the copied path and hit the enter button. So this command is used to change the current directory to the code folder's path. So now compile the app.py file using the command python space app.py. I am typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, local host and port unless configured differently. Now copy the local link provided by the framework. I am copying it and paste it into any web browser. I prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. So here we can see a sign up link, click on it. So if we are new users, we have to register first. Fill in all these details and click on register button to sign up. And if we already have an account, we can directly log in by clicking on this link. So as I already have an account, I am clicking on this link. So here we have to provide our credentials, username and password. And click on login button. So it has redirected us to the detection page. So now we have to fill in these parameters and click on predict button to get the detections. First we'll understand these parameters. So the first one is L4 SRC port, that is source port. So it identifies the origin port for data. This is L4 DST port, that is destination port. It designates the target port for data delivery. This is protocol. It specifies the communication protocol, example TCP, UDP, etc. This is L7 proto, that is app layer protocol. It indicates the application layer protocol. This is in bytes, that means incoming bytes. It measures received data volume. This is out bytes, that is outgoing bytes, which quantifies transmitted data volume. This is in PKTS, that is incoming packets, that counts received data units. This is out packets, that is outgoing packets, which enumerates transmitted data units. And this is TCP flags, which signifies control functions in TCP headers. And this is flow duration milliseconds, which represents flow duration in milliseconds. So now we'll fill in these parameters. So L for SRC port would be 57442. L for DST port would be 15600. Protocol would be 17. L7 proto is 0. In bytes would be 63. Out bytes would be 0. In packets would be 1. Out packets would be 0. TCP flags would be 0. And flow duration milliseconds would be 0. Now click on predict button. So here we can see the result, that is there is no attack detected and it is normal. So click on home link. We'll try again giving another set of parameters. So this time L for SRC port would be 60641. L for DST port would be 53. Protocol would be 17. L7 proto would be 5. In bytes would be 108. Out bytes would be 108. In packets would be 2. Out packets would be 2. TCP flags would be 0 and flow duration milliseconds would be 4. Now click on predict button. So here we can see the outcome, that is attack is detected and it is DOS attack or other attack. Similarly, we can give any set of parameters and can get the detections. So we'll try again. So this time L for SRC port would be 42075. L for DST port would be 53. Protocol would be 17. L7 proto would be 5. In bytes would be 108. Out bytes would be 108. In packets would be 2. Out packets would be 2. TCP flags is 0 and flow duration milliseconds would be 3. Now click on predict button. So here we can see the detection, that is attack is detected and it is DOS or other attack. So the attack is detected. Now click on sign out link. So the conclusion here is the project successfully addressed the complexity of Internet of Things security, showcasing the efficacy of multitask LSTM based model in detecting evolving malware threats. By incorporating dataset heterogeneity, the model demonstrated adaptability to various Internet of Things scenarios, ensuring robust intrusion detection across a spectrum of devices and cyber attacks. By leveraging LSTM networks, facilitated a leap forward in analyzing time series data, enhancing the model's ability to grasp nuanced patterns in Internet of Things network traffic. Bridging the gap between theory and practice, the project provided a tangible solution with user-friendly Flask frontend, empowering users to interact with and assess the model's predictions. And the extension involving CNN and a hybrid model showcased innovation in combining multiple models for a more accurate final prediction, underscoring the project's commitment to cutting-edge solutions in Internet of Things security.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.